It's okay. Now it's time, and 1 minute late, and I'll begin. Welcome everyone. This time, this is checkpoint 80% of my PhD, and I'm going to be talking about again probabilistic human communications and its synthesis and spices, like I always do. And that's this will be presented by me, and I'm supervised by Gustav and Jonas. We've been maniacally adding more and more spices to the base probability salad that we started creating from the start of my PhD. Okay, so the ingredients of today's presentation would be, I will give a quick recap of my last presentation, what I did. It's a lot of stuff. I will try to go fast. And I'll talk about the new spices that we have fused, invented, generated. Some of them include Matcha-TTS, Match-TTSG, work on stochastic duration predictor, and MAGI. I refuse to call it MAGI. And what I'll be up to next, and yeah, from there we'll take it. But first I'll begin, I'll want to argue that what my research goal has been since the beginning of my PhD. I come from a software engineering background. I really like making things that work, like as in software and stuff. So I always wanted to create something that's useful for researchers, people, and eventually we have tried to at least get closer to that. And also we've been always focusing on something that doesn't require one to have infinite computation resources and or a lot of data for someone to use it and say that, oh, I work as an AI researcher, or I generate things with AI. But also, most importantly, the main motivation for me to work in something like speech synthesis is
to clone my own voice so that I can send stupid audio messages to my friends and supervisors and blame it all on AI.
so. This has been one of the biggest motivation. So quick recap. I'm gonna give what I've been doing till 2023 before till my 50% presentation. It's we worked on neural HMM-TTS. At this point, this must be very redundant to almost 90% of you. So I will really make it very short. That we knew neural text-to-speech after Tacotron got very powerful. They had the highly natural sounding speech, but they had the attention, and the attention in attention-based autoregressive architecture like Tacotron 2 was very slow to train and could break down, or required a lot of data to train on. So Gustav had a very cool idea to fuse hidden Markov models. Before the neural paradigm, there used to be SPSS, hidden Markov model-based text-to-speech synthesis, which generate a bit metallic sounding speech and required a lot of hand-picked feature processing. But the good thing about this was it used to rapidly learn to align, and it required very little training data. So good idea of Gustav was to fuse these two and get the best of both worlds. So we took the neural network from neural TTS, we took the HMM from the HMM, and then we fused them and created neural HMM TTS, which was which resulted in highly natural sounding. It would rapidly learn to align, does need a lot of data, and was pretty cool. Yeah, you would get intelligible speech within 1 hour of training, and even with just 500 utterances. It was very cool at that time because Takatron 2 would never learn to align with the little data. And we presented at ICASSP in Singapore 2022. That's when the journey began. Then Harm, you remember, our survey of the year, customer of the year. He said that I will use this neural HMM TTS and generate controllable speech by conditioning it on different things like F0, the variation in F0, like some deviation we used, and speech rate. So he added those 3 extra features and passed it as an input, and then we could generate more controllable synthesis. There's more on this on his talk, but we present this in ICASS 2023. And then the problem with neural HMM TTS that we found was that we assumed the speech acoustics to be Gaussian there. We were generating Gaussian parameters, mean and standard deviation. But unfortunately, the things lie in a more complicated distribution in some high-dimensional space. So normalizing flows were cool. They could model these complicated distributions with the higher precision. than at least Gaussian distributions. So we sort of added normalizing flows on top of neural HMM-TTS. So now they're sampling latents, and once we sample all the latents, it passes through an invertible transformation and get like a more complicated or complex distribution, which resulted in very high quality and had all the benefits of neural HMM-TTS with more modeling power. And we presented this at the Interspeech 2023. So the idea was to create something usable for researchers, and all the source code was fully hackable and open source. Got a lot of attention on GitHub. We started getting stars and forks, and people even made research papers out of it. And I also integrated them in open source library, making it as simple as like just pip install TTS and put the model name, and then you can just get synthesis out of it. It was merged in Kukui, which now I think has like 30,000 stars. So it was quite nice. And as I said, it doesn't require a lot of data to train your own system. So a couple of papers that had released the data set, but the data set was small, they used overflow to sort of just put the data out. Well, I worked with Ambika with the stuck in MOSFET because every time we were running evaluations, it was getting very hard to reproduce those baselines because subjective. So Ambika said that I will explore what the mystery is. And then she came out with amazing conclusions that there were a lot of inconsistencies around MOS evaluations. People would not disclose the demographic, the scale used. And because of these differences, the results were, basically, that was me crying all the time, stuck in that MOSFET. So in that paper, we made some suggestions and recommendations to solve how to resolve some inconsistencies. Yes, the next Diff-TTSG. This is the last paper where I ended my last year's presentation. Is that we with an amazing team with an amazing score matching approach. We generated multimodal speech and gesture. That's oh, that's not the generated gesture. That's me. That's me presenting the paper in SSW. But the idea was, you use the score matching to denoise both speech and gesture into different parallel approaches. So one way, you will take an average Mel spectrogram, it will generate gestures. You take an average Mel spectrogram, it will generate audio. And now, what I've been up to in the last year. So after generating a couple of gestures, I started calling myself a gesture generation researcher.
Now I am a gesture generation researcher.
I had a swag in the department walking around, and everything was going fine. I was blending in until one day the gesture generation group came and they were like, "We heard you do gesture synthesis now. Want to join hands for the Genia challenge?" And I was like, "Damn it! I need to fake it to make it." There's a callback to a paper that will come later, and like, yes. But it worked out fine. We presented a paper, diffusion-based co-speech and gesture generation using joint text and audio representation. Anna did an amazing job at taking the lead at it. We came up with a two-step approach where we sort of trained a clip type model. But in this contrastive approach, we tried to align input audio and text into a representation that is shared with motion. So during the generation, we don't have this motion. We'll just put input text and audio, and then we will condition this to a diffusion process. I think in this case with DDPM, and we get the highly natural sounding gesture. And it kind of worked because we sort of performed best in the human likelihood study. So then my gesture generation side was also. I will later recruit more people into the gesture generation group. I'll talk about this. So then after this, Gustav and we were having a very serious discussion, like we always have. And like Gustav goes in, like the fusion for TTS is amazing and all, but I want it to be a bit more faster. And then
I
go
heard
like,
about something called flow matching. How about we try to match the flows?
and like let's match the flows. And quickly the serious discussion turned into not so serious discussion. Gustav goes and does flow matching, and then I'm like, yes, flow matching. And then Rubu joined us as well, and we all were doing flow matching at the same time. So Yes, then with the help of Eva and Jonas, who also joined us within our flow matching adventure, we came up with Matcha-TTS. It will be the most meatiest part of the presentation because this will basically, yeah, one of the nicest thing that I think I've come up with during my PhD. And so Matcha-TTS, it has two components. It's based on conditional flow matching, as we just talked about, and it's a fast TTS architecture. So I will break down both of these components and go into a bit more depth of what these two are about. So we'll go with a bit of background, conditional flow matching from diffusion and normalizing flows. Diffusion models are great. You train them, you add noise and try to predict this noise, and they have resulted very good output. And normalizing flows were super cool as well. They had a very good maximum likelihood estimation principle. You could take a noise and then transform into any complex distribution. Let's dig deep. So diffusion models at this point, everyone will agree, are a powerful generative model and state of the art in almost every field that involves sampling from a continuous distribution. It could be text to image, text to speech, or even text to video. So everyone has been just putting more and more parameters into a diffusion model, and like here from Sora, this OpenAI's biggest video generator, to good speech model and whatnot, tortoise, and mainly because they're very easy to train. You do not need to deal with these like tails of the likelihoods and infinite likelihoods. All you have to do is just do a mean square error on a regression loss or on a noise on sample noise, which is very cool to train on. But one problem with them is that, as Gustav was telling me during our serious discussion, that they are very slow to sample because of these iterative refinements, and they often required 100, if not thousands, of steps of denoising. So we needed to speed up for reusability for using them because everyone has used them already, and some people come up with better schedulers and faster solvers. Wait, my solvers disappeared, but this faster solvers. This from Stable Diffusion, they have integrated a lot of solvers there. People tried distillation, where people would try to distill a large network into a smaller one to make it computationally faster, or formulate the entire process as a continuous SDE or ODE process, where you have from instead of 1, 2, 3, 4, 5, and 1,000 individual steps, you try say that everything will be between 0 and 1, and then you can interpolate very nice. Like, give me at 0.3 how much noise image will be. Give me at 0.8 how much noisy the image will be. So nicer interpolation properties have in that. And going back to discrete normalizing flows, it's a series of invertible transformations. You at time step 1, you start with the very random noise, and eventually you morph that, squish it, flatten it, and beat that noise, and you convert it into the distribution you want. Given you keep track of how much probability mass you've taken or inserted into that space. And so essentially you morph the distribution per discrete time step. This is the discrete part of these bracketed discrete normalizing flows. But the problem was this invertibility was very expensive. You need to compute this determinant of Jacobian in high dimensions. For some reason, my dimension disappeared. So this log of determinant, it's very complicated to compute when the dimensions get super high. You have to spend more time computing this than to actually solve the problem. So people come up with like they needed to trade off this computation for how much expressivity your network could have. So they developed some smart hacky ways for computing this determinant, and which resulted in suboptimal or limited expressivity. Then came these continuous normalizing flows, which continues to flow matching and everything. Is that what if instead of having these discrete modes, we take this continuity equation from fluid dynamics, where the change in this probability density at each small time step, which is the denominator, is equals to this divergence of the vector field, which is like how much things will change if I will take a very small time step. How much things will change in a probability space if I take a very small time step. And I learned this change. So the flow of data from one point to other, basically. You can, and at each point you follow this Navier-Stokes equation from fluid dynamics, which says that you will conserve the probability mass. You will not add anything. You will not take away anything, reverse gestures, but you basically flow this data point from one to other, which is called flow matching. And then so the idea is that this vector field that was flowing the data points you learn that you do a mean square error on this vector field, and like you regress on the score of distribution in score matching. This time you regress on this vector field, and because there is no deterministic, no randomness during the flow, you can make it a simpler problem. You solve a ordinary differential equation instead of a stochastic differential equation. So you sample a noise, and then you just take that noise towards your data. You sample another noise, you take that noise towards your data, and then that's how you sort of generate samples. And conditional flow matching is a part of it because things are easier to compute. So the point is that you take each individual Gaussian. So you say that, oh, this is a Gaussian. At time step 0, what I have is Gaussian. At time step 1, what I have is data. I will take this Gaussian and put it on top of my data. I will take this Gaussian and I'll put it top of my data. And then you learn to regress on this this transport field or vector field in this sense. So you basically move this Gaussian separately and you put on top of it. And you learn this red vector field, like how it is transforming towards stuff. And one of the easiest ways to do it optimal transport, because to form a line between them, so change mean and standard deviation sort of linearly in time. So you have a very tiny Gaussian sitting on each individual data point, and you learn how to get an average of it. So people used, when it came out last year, it became a big hit. People used it to solve complicated problems. TTS, in our case, it became a voice flow, Matcha-TTS, reflow TTS. We were lucky that we published we at least put our paper on arXiv on first, and suddenly once our paper was out, after a week or two, there were like 2-3 consecutive papers that popped up doing almost the similar things, calling it differently. People did few shot TTS. NVIDIA came up with pflow using almost the same architecture and the same approach, but they added like another speaker encoder so that you can generate for different speakers. And Meta came up with the voice box, where they said that we have data, we have compute, we will create a universal speech editing architecture, which used flow matching as a background set. So flow matching was fast, but we're greedy people. We always need more speed. And so there was a room for improvement. To improve synthesis of speed of these flows, people have come up with the rectification of flow, which basically is a two-step training process. You further straighten the path. So you first you train the model, the flow matching model with the same math, and then you save the noise and the data point. And then instead of sampling randomly during the training, you use those as pairs. And then once you learn this, you also, again, further straighten the paths for this. Meta came up with an improved solver called bespoke solver, which you sort of like transform it to a different space, which is easier to solve. You solve it there and you transform it back. And this transformation was invertible and learnable. And then people came up that improved the architecture, and those people were us. So when we think of fast TTS architecture, anyone who works with TTS, the first name that comes into the head is fast speech because fast, or fast speech because fast. It's in the name, I believe it. But the core of this fast is these highly efficient, memory efficient and fast feed-forward transformers. They also had these sinusoidal position embeddings that could not, like the normal problem of transformers, they could not extrapolate very well, but they were non-trainable, and that made things faster. But both of these architectures, they used the mean square error loss, which is like non-probabilistic. So they would not learn a distribution over the speech acoustics. They will have just for same input, there will be always the same output. It was deterministic. I will talk a bit more about in one of our works with this. So basically, I think it's time to now finally introduce Matcha-TTS. Hopefully, you will also see as a logical path that one could have taken. That we said that, okay, transformers are fast. We will put transformers everywhere. We need something that's non-trainable and can extrapolate. Rope worked because later found out like Llama and Mistral and whatnot, they also use rope embeddings to extrapolate and make it non-trainable and fast. And it's a very cool hack monotonic alignment search that exists in TTS literature to learn to align, which is very fast and does the job very pretty well. And then took inspiration from stable diffusion, and wherever I saw 2D convolutions, I started replacing them with 1D convolutions. and made a very similar UNet, which being transformers at the core of it, transformers and convolutions, being fully parallel was super fast on GPUs. And this generated probabilistic and highly intelligible speech with the speed as fast as 0.05 real time, which essentially rivals those fastest TTS architecture, which are suboptimal to relative to Matcha-TTS. Yeah, so a bit of experimentation and result. We did our experiments on LJ speech because if you don't do, you don't get accepted. This is the MNIST of TTS. So configuration, we had this vocoded speech. We made sort of like an upper bound. We used the vocoder to just convert the raw Mel spectrum, like reference Mel spectrogram into waveforms. And then we use VATS, which is a probabilistic end-to-end architecture. So you don't have these two components. Generally, you divide it into acoustic model and vocoders, and this had both inbuilt. So as to compare against the end-to-end system. We had the GRAD-TTS, which is a probabilistic acoustic model. And we also had an ablation where we put flow matching in GRAD-TTS. GRAD-TTS on its own uses score matching. And we had the Matcha-TTS. Oh, we also had fast speech too. I don't know why it ran. So fast speech too, which is a deterministic acoustic model. So we covered like an entire umbrella of things that we wanted to compare with. So it turns out that Matcha-TTS achieves, oh, I don't know why the typo, but it achieves high naturalness and intelligibility while it maintains the smallest memory footprint with fast synthesis speed. So it's one of the fastest and gives very high naturalness. And being probabilistic, you get all the benefits of being probabilistic. And if you go like low diffusion steps, or low denoising steps, or low number of flowing steps, for 2 and 4, it's even faster than fast speech 2 for like longer utterances. So transformers being quadratic, fast speech has blocks of transformer, but us being a UNet architecture, we gain some advantages when we have less channels somewhere. Some audio samples. So you would see the benefit of flow matching approach is like even when I go as low as one step, the speech is still intelligible. It's not random noise. I will start from 10 to 1 and try to not to speak in between. You will only find the bit problem in one step, but otherwise it's almost indistinguishable, at least for my ears, between 10 and 2.
The narrative of these events is based.
Wait. It is really indistinguishable.
The narrative of these events is based largely on the recollections of the participants. The narrative of these events is based largely on the recollections of the participants. The narrative of these events is based largely on the recollections of the participants. The narrative of these events is based largely on the recollections of the participants.
So it's super fast, and pretty good with just one denoising step. Another sentence, so to make you believe.
The jury did not believe him, and the verdict was for the defendants. The jury did not believe him, and the verdict was for the defendants. The jury did not believe him, and the verdict was for the defendants. The jury did not believe him, and the verdict was for the defendants.
And also the best part, can you use it? Yes, you can. It's again fully hackable. It has over 400 stars. If you don't want to clone it, you can just pip install it. Do a pip install Matcha-TTS, and then you have it. You also have a Gradio interface if you do Matcha-TTS app, or even lazy, just go on Hugging Face. You can run it on GPU. You have a space running there. Super cool. I think that goes back to again the research objective to create something that's useful for people or researchers. Matcha-TTS, a blind community called Blind Pandas, they reached out to me and they use Matcha-TTS as their on-screen reader. So because it's fast locally, you don't really need GPUs. If you replace the vocoder from Hi-Fi GAN to Vucos or any CPU heavy vocoder, it's faster than real time on CPU. So it has it turned out to be one of the nice. That's why I said one of the nice things that came out of my PhD thesis is that or research is that we made Matcha-TTS. Very happy about this. One fun sample trailer that I made, which is stupid but fun, and I think everyone should see.
Once upon a time, in an old tavern.
If only I had a TTS architecture that is probabilistic.
And also has a compact memory footprint.
But I also want it to sound highly natural.
Wouldn't it be amazing if,
It is also very fast to synthesize from.
Too many demands. We need a solution.
Have you heard about Matcha-TTS?
What is it?
Tell us.
Tell us. I mean, that it's nothing that fancy. It's just useful.
It is Matcha-TTS. It's a fast TTS architecture with conditional flow matching.
Scan the QR code or visit the link for more information about whisking Matcha-TTS.
All the samples were generated by Matcha-TTS, of course, and then, yeah, fun. Empty mind is devil's mind. So when I'm free, I do stupid stuff. But that's it. Then, once we got flow matching figured out, I ran to Simon. I was like, let's make this TTSG better and faster using flow matching. And then Simon says, I'm listening, denoising, and now I will do some action about it. And I think that, did he just low-key advertise the LDA paper? Nice. So we talked about what has been done before. In multimodal synthesis between speech and gesture, Simon and everyone was first to chain together a deep learning architecture to make it. But the problem was it required pre-trained components. And then Sian came up with integrated speech and gesture synthesis that did both of the tasks in the same neural network. But it again required you pre-train some component, freeze the other one, then you freeze the first one, and then you train the other one. So it had a bit of hacks. Then we came up with the Diffs-TTSG, but the problem was the two pipeline approach. So once you have an average spectrogram, you will send it to motion, and then you will generate speech separately. The speech would have no connections with the motion, or motion would not have connection with the speech. It would have from the average speech. So it was not the most efficient one. Yeah, I had two parallel pipelines, which made less coherence. So in short, we created the Match-TTSG, where we used text-edited input and used a joint architecture this time with the help of conditional flow matching to generate both speech and gesture. And this resulted in end-to-end, fast, probabilistic, and it did not even require a lot of training data to generate both speech and gestures. And it was so fast that it's actually real time. So you can put like a ChatGPT backend, and you real-time get real-time generation of speech and gesture both, if you figure out how the visualization works, which is the pain of my existence. Yeah. So how to train a Match-TTSG system? We did nothing fancy, basically. We just took the 80 MEL spectrogram channels and concatenated the 45 motion channels, and then put an input text, phonetize it, encode it, use this monotonic alignment search, which is basically Viterbi algorithm to align text and these concatenated audio and motion representation. And you train a neural network that during training mimics as a proxy to just learn this monotonic alignment. So once you are generating, you just synthesize from it, and you use the conditional flow matching to learn the distribution over the target input. And how to generate from it is similarly, you input text, get alignments from the duration predictor, and then you just sample iteratively and use a vocoder to transform MEL into a waveform, and some sort of motion visualization to visualize the generated gestures. Evaluation for this is a bit complicated because you have the components we use is we basically compared against our own base state of the art to create new state of the art. And we use our new architecture with score matching to ablate about the effectiveness of flow matching in this architecture. And then we had our final Match-TTSG. We did a speech only evaluation where we just we hit the other modality and only generated speech. We generated both modalities, but evaluated only speech. Then we did a motion only evaluation to see how realistic the motion was. Is it a jerky or like weird motion like this, which I got once when I was experimenting with stuff. And also the appropriate evaluation, which like we would show both videos side to side, one with the matching audio and video, and one with the swapped video. So the audio was in.
When you think about it, that you do as a child. When you think about it, that you do as a child is just absolutely ridiculous. That makes no sense. But you can always justify it back then because it just seemed like the fun, right thing to do.
Okay. For some reason, the other one, there's a mismatch one, which didn't play, but never mind. But the proposed model is significantly better than previous state of the art. And even with like just 10 denoising step, it's like when we were training the Diffs-TTSG, it required at least 500 steps to generate the jerk-free motion. Otherwise, it would be like. So in this case, because being the benefits of flow matching, it would just generate it in 10 steps and without any jerks and everything. So it was very cool. And because of having one architecture instead of two pipeline, the speech and motion was had more coherence among each other. We also did some object evaluation, which is like the new architecture was smaller than the one because two components were merged into one. It consumed even less memory while training due to the effectiveness of convolutions and transformers. It achieved faster than real-time synthesis and had very less word error rate, despite being 10 times faster. So, an example.
And they finished, they cleaned up the wound and stuff. I stood up and I just collapsed onto the ground and fainted because I was completely drained of all my energy about everything. Like, it was absolutely, so bad.
So yeah, it had a bit of coherence, so you could see those beats very nicely. Then one day, again, during our experiments, Gustav, flow matching is so fast. What if we also try to put it in the duration predictor? He was like, do you mean there will be more probability in the probability salad? I'm like, yes. And Gustav's like, oh, yes. I could definitely imagine us having this conversation. So I started working on it. It's just dramatic effect. All I was doing is like torch import. But then one Indian guy named Rajiv, who was living in South Korea, where ICASSP was going to happen, reached out to me on Discord because of Matcha-TTS, and he's like, I love Matcha-TTS, and I'm like, what a coincidence, me too. And he's like, have you tried putting flow matching in the duration predictor? And I was doing it. I'm like, this is literally what I'm doing right now. Want to do it together? And he's like, yes, awesome. And then Harm said that he also likes duration predictors. So we came together. You remember Harm, the Subway's customer of the year. And so we came with the paper together and it's like, should you use a probabilistic duration model in TTS? Probably, especially for spontaneous speech. So essentially in general, most of the known autoregressive text-to-speech architecture have this component of duration predictor because things are happening in a parallel fashion. They do not have a feedback from the generatic acoustics. They try to predict the duration of the entire MEL or any other audio representation in one pass. So this is the one component that's responsible for upsampling these discrete text tokens into a continuous audio representation. And a widely adopted approach is to have a network and just do a mean square error on it. So make it deterministic. But when I speak, I don't always say hello for exactly 4 seconds. 4 seconds is a bit over exaggerated hello. But I have a lot of variation when I'm trying to even say hello, and stuff like that, or maybe hello, depending on where I am. So instead of learning a point estimate that here's the mean and this is what you get, we try to learn the duration distribution over these utterances. So we had because flow matching was fast, we could do it in 10 steps. So we're like, let's replace this mean square error and put a flow matching loss there. And it worked out pretty good. We compared two corpora, two being spontaneous speech and two read speech. This is submitted to InSpeech. It's currently under final meta review, so hopefully the result will be out on 6th of June. But the point is we'd use the LJ speech and Ryan speech as red corpora, and Trinity speech and gesture 2, and apartment speech from Demos as spontaneous corpora. And with 3 different architectures, we tested this duration predictor. Again, we use these different components where fast speech 2 is a deterministic acoustic model, VITS is a probabilistic end-to-end architecture, and Matcha, because there was the easiest source code available on the internet, self-plug, a probabilistic acoustic model. And our conclusions were that if your architecture is probabilistic, it almost never hurts to have a probabilistic duration predictor. It's even better if your corpora has, or if your corpus has these disfluencies and different variances, then a probabilistic duration predictor will capture this variance in much better way than having a point estimate of it. And a model trained with the aim to reduce mean square error, it terribly suffers. It doesn't learn to account for these randomness, and then it just shuts down the moment you add the probabilistic duration predictor. And LJ speech, which is the most widely used corpus for text-to-speech evaluation, we don't know why. may not be the best benchmark for duration and process evaluation because of the nature of speech. It's a read speech. People say that we have better prosody with LJ speech. The LJ speech in itself has bad prosody. So rant over. But yeah, this is some sort of conclusions we made with the results. And then one day Jonas said that we should use Matcha-TTS, and Christina also joined hands, and they were like, we should use Matcha-TTS to generate the speech using continuous phonological features. He says that, do you think Matcha can do it? And me being always over enthusiastic, I'm like, yes, it can. And Jan said, okay, I approve it. Yeah, we can play with it. And it actually worked out well. Christina also submitted it to Interspeech, and very, very kindly, even though I did nothing in this, just give like here's a source code that runs. So the idea is that she converted phonemes into phonological features between 0 to 1, and then trained the Matcha-TTS with those phonological features, these continuous features, and then cool phonetic analysis, which Christina can tell you more about it because I only know this part. No, but it's her paper. She definitely knows much more about it than I do. And then I came up with a plan. This is again the cool gesture generation group. I said to Birrer and Jim, I'm like, guys, I have sources. I can get you in. And then I'm like, yes, I want in. And then we prepared a lot of intensive physical training. And obviously hugged, and we were ready and then we came up with this paper called Fake It to Make It, where we use synthetic data to remedy the data shortage in joint multimodal speech and gesture synthesis, where we said that there have been two parallel paradigms, one text to speech and other speech to gestures, and they both have at this point they're generating state of the art performance in both of the fields. So we said, why don't we generate a lot of synthetic data? So we generated spontaneous text from ChatGPT-4 using different prompts about like different situations. Tell me about zoo, get surprised, be angry and stuff. And then we generated the multi-speaker speech and filtered it extensively. That's where Jim with his crazy good scripts came into the bar. He's like, I will filter the data, don't worry about it. And then we generated a lot of motion from this generated synthetic this speech. And then we sort of had the mitigation for the problem of limited trimodal dataset, which is the problem of Match-TTSG type of approach. And then we can just pre-train this Match-TTSG on a large corpus of data, which is synthetic. So it's more of like a weak supervision or distillation of those state-of-the-art models. But you pre-train a probabilistic multimodal generating model with this synthetic data, and we have 3.5 hours of human recorded data for this, and then we just fine-tune on that. And the results again were pretty decent. We saw that pre-training actually helped to reduce the gap between natural and generated speech and gestures. There were some architectural changes, but I think this is the more fun part, that being modern generative architecture so powerful, you could actually proxy synthetic data to pre-train the architecture like this. And yeah, that's what I've been up to till now, 40 minutes in. But what next? This year has been very lucky. I'm going for some industry internships to learn how industry tackles a problem when they have resources at hand. I'm going to Microsoft and then Meta, and I'm going to put the H in Meta. Yeah, and yeah, I think thank you for attending my seminar. You guys rock, each and every one of you. Thank you very much for attending this seminar and being part of my PhD journey. I'm deeply grateful for my supervisors and everyone who's been involved with me at this point. Your support has been amazing with everything that's been going on with the bureaucracy, papers, money, in every sense, been amazing. Special shout out again to professors, teachers, supervisors here at TMH. I really appreciate the fact how accessible and helpful everyone is. And thank you for my wife for dealing with me and my parents and friends. I love you guys all. And again, RIP 509 fridge is taken from us. gone from 509, but always in our heart, and perhaps in the basement still. That's it. That's all I have. Yeah, thank you.